So we've been doing a lot of math, a lot of calculations. I can dim this light a little bit more. Hard to see. Chapter 9, we take a break from all of those calculations and talk again more conceptually about electrons and atoms and the structure of the atom. And we're going to talk about a bunch of historical models and talk a little bit about electromagnetic radiation, light. So all light is electromagnetic radiation. It is the same fundamental thing as what allows you to watch TikTok on your phone from anywhere, right? It's the same thing, just at different energy levels. So that being said, don't forget about, and that's part of what the weekly quizzes are supposed to do, is they're supposed to be like a, hey, you remember this thing we did a while ago? Because the math is all going to come back after we talk more about structure of atoms. And hopefully we can use this stuff about electrons and atoms and the periodic table to explain some of the stuff that I've just had you memorize. This gives more of the reason why something like sodium forms a 1+ charge, the reason that silver is a 1+ charge, or that chlorine is a 1- charge. All has to do with electrons around the atom. So you may have heard of the Hindenburg. Has anybody not heard of the Hindenburg? Big blimp, caught on fire. They filled it with hydrogen, which is a dangerous thing to do because hydrogen is flammable. Tragically killed 36 of the 97 passengers. Amazing that anybody survived. I think it was a thermite reaction in the paint was one of the theories as to why it initially caught fire. So what is it that makes hydrogen so flammable, reactive and flammable? That's part of what we're going to talk about. And then why is helium, because we'll have hydrogen on one end of the periodic table and helium on the other end of the periodic table. They're very similar. Helium has one more proton, 2 more neutrons than hydrogen. But you'd think that being so close together, they'd also have similar properties. Even though helium doesn't burn. That's why we usually fill party balloons with helium and not hydrogen. Because again, balloons full of hydrogen plus birthday candles is a bad combination. So modern blimps are filled with helium. And so we'll talk about that. Like, why is this helium inert? Why is hydrogen reactive? And other elements on the periodic table also. And actually, if you look at the periodic table, we talked about this a little bit earlier on, but the reactivity exhibited by hydrogen is also seen in all the other group 1 elements in that same part of the periodic table, in that same column. And then helium, is part of the reasons put on the other side of the periodic table from hydrogen, is because it reacts and behaves like the other noble gases. So all of those gases in that column behave the same way, and that turns out to be because of the electrons. We're going to go over some of the history of the atom and like how these models were developed. Actually saw a video recently complaining about how in chemistry there's a lot of times where it's like you get told one thing and then you get immediately told that was wrong and this other thing is true, and then you get told that was wrong and this other thing is true. I want to lead when we talk about these models. We're talking about it from a historical perspective. And so as we go through that part, I'm not going to really expect you to know those things about the more outdated models. But I do think it is interesting to talk about the history and how the original chemists, how scientists worked all of these things out, and the reasons that they thought they had a good model of the atom, and then why that was proven to not be enough, and why new models were needed. So the Bohr model is one. The quantum mechanical model, that is the most modern, most current, most correct model that we have. And both of those models, to a certain extent, explain periodic law. Basically, when you arrange the atoms in order of increasing atomic number, then you get these sets of properties that recur periodically. And actually, if I just flip over to the periodic table, see, so we just look at this periodic table, right? I mean, starting at the top, it goes 1. So the first element, hydrogen, very reactive. Helium, not reactive at all. That's why they get put on opposite sides. But then when we start here, lithium, the first element, now, if we start a new row, very reactive. Still reactive, but less reactive for beryllium. Come over here, and we get less reactive, and then we start getting more reactive again, and then we get to neon. And again, we talked about charges. I just had you memorize these. But fluorine, 1-, oxygen, 2-, nitrogen, 3-. By the time we get to neons, oh, we got to another inert element. Let's start another row. And then if you start another row, on 1, sodium, again, reactive. Again, less reactive, similar to the jump from lithium to beryllium, sodium to magnesium. And we get aluminum, which again, our reactivity like dips in the middle and then it starts to get more reactive. And then our charges also reoccur. When we get to phosphorus, that's 3 minus, sulfur's 2 minus, chlorine's 1 minus. And then we get another element that's inert. And this is something that just, it's not like people decided, not like somebody decided that lithium was going to be a reactive element. They just said, we're going to put these in order. And then it turns out, starting in the second row, every 8th element is inert. Every first element is reactive, and that pattern repeats. It changes a little bit as we get higher up, and so we'll see why that repeats, or why that pattern changes too. You've had to memorize a lot of just things about atoms. They do this, they do that. Hopefully now we can present the why. We can say, this is the reason that I had you memorize these rules. When we get to talking about the quantum mechanical model, a lot of famous scientists really didn't like it. Niels Bohr, anyone who is not shocked by quantum mechanics has not understood it. Erwin Schrödinger, I don't like it, and I am sorry I ever had anything to do with it. And then Albert Einstein, God does not play dice with the universe. And this has to do with, when you look at the quantum mechanical model, it's actually not too far off Marvel's interpretation of the quantum realm. When you get down to things that are small enough, things get weird. And our idea of physics at the macro, larger scale don't apply to things at this much, much smaller scale. And when we talk about electrons, that is very much the case. They do not behave like a particle like you might have seen in cartoons, or if you see a drawing where it's a nucleus, and then you've got these electrons on these rings around the outside. They don't do that. They don't do anything really even close to that. It's spooky. The quantum mechanical model is, again, the most modern. It's the basis for the modern periodic table, guides our understanding of chemical bonding. We'll talk about how to predict the structures of different inorganic molecules and a couple organic ones. And really, this is now, it's part of everything. Any kind of material science has some sort of chemistry in it, right? The plastics that make up, well, plastic or the metal or anything to do with any computer, any device that you use, your clothing has chemistry in it, your car has chemistry in it. And a lot of it is based on discoveries with quantum mechanics and really fundamentally understanding how elements interact. Even the fact that you can have blue LEDs. But before we really get into any of that, we have to understand light, what light does and how light works. So light and electromagnetic radiation are the same thing. I should say light is a specific band of electromagnetic radiation. It's actually a very small piece of the whole spectrum. So it's a type of energy, actually. Light is not matter. It travels through space at a constant speed of 3.8 times 10 to the 3.0 times 10 to the 8 meters per second, which is about 186,000 miles per second, which, where's my calculator? I don't really need it today, but just so we have a better idea, because I know, like you, I too think in miles per hour. So 186,000 times 60 would be minutes, times another 60 would be hours. Whoops. 160 too many. So it's 6.8 times 10 to the 8, or sorry, 6.7 times 10 to the 8 miles per hour, which is an unfathomable speed. And actually it's seen as the speed limit of the universe. Nothing can go faster than that. So light is moving very fast. This is the reason, actually, maybe you've never thought about this. I'm a big old nerd, so I've thought about it. It's like, how does the cell tower know where your phone is when you're driving in a car at 80 miles an hour? Right, you can get text messages and then go back to the tower. That's fine. You can do things instantaneously. You can have a Zoom call on your phone while you're driving. Don't do it while you're driving. Somebody else is driving, right? That's because this speed means that the speed of you moving means nothing because it's going at, again, 6.7 times 10 to the 8 miles per hour, whereas you're driving 80. Anyways, light is moving real fast. Does not have mass, or does not have matter, is not matter. It does not have mass. Light has properties of both waves and particles, which is another weird property of light we won't go too much into. So just like a water surface, if you disturb the surface of water, it creates these ripples. Those ripples are caused by the energy that whatever you threw into the water has imparted in the water. So when your phone sends out a text message, it sends out a ripple in 3 dimensions away from you, and part of that hits the cell tower, and then your text message gets sent. So your phone is transmitting, and it's using energy, and that energy is creating these waves, and so we can transmit messages on that energy. So because it's a wave, just like waves in water, we can measure something called a wavelength. And again, these waves are happening in 3 dimensions. We're just going to be looking at a 2-dimensional version of it. The wavelength is going to oscillate from a low energy to a high energy and back to a low energy, and it goes through this same cycle over and over again. The wavelength is the distance between 2 points of the same energy on that wave. Usually a crest to a crest, so the peak of the wave is a crest, the bottom of the wave is a trough. So if I measure from a trough to a trough, it'll be the same as the distance from a crest to a crest, or a peak to a peak. Or I can measure from here where it crosses as it's going up, to here where it's also crossing as it goes up. So that's the wavelength, the distance between those oscillations. A lot of times we can talk about wavelength when we're talking about color. So the wavelength of a laser pointer. Do I have my laser pointer? I have my laser pointer. I got a red laser pointer. I should use this more often. Forget that I have it sometimes. So this one is, have I worn it off? Is about 650 nanometers plus or minus 10. So the wavelength of my laser, if we were measuring it, this would be 650 nanometers. So we can measure the distance. If you change that wavelength, it'll change the color of the light. Most lights are a light from the sun or light from a light source like an incandescent light bulb and a white, now most light bulbs are LEDs, a white LED light bulb. It's got all of the different wavelengths in it in the continuous spectrum of color. And you can send that through a prism, and then you've got that, was it Pink Floyd? Is the cover? Album cover? No? They have a prism? Yeah. So you shine it through a prism, and it separates out all these different wavelengths. And so you can get individually red light, or all the way up to violet light, or anything in between. And they get bent more by the prism depending on their wavelength. So longer wavelengths get bent less, shorter wavelengths get bent more. And then when you're looking at something, this is weird to think about, but when you're looking at something, it's red only because it's reflecting red light. It's actually absorbing all of the other frequencies of light. This is why a black car or any dark colored car is going to get really hot, because it's absorbing all of the frequencies of light, whereas a white car is reflecting all of the frequencies of light. So anything that you're looking at, you're seeing the color that it reflects. All right, so we talked about wavelength, and that's easy to think about when you've got a wave that's standing still. But these waves are never standing still. They're always moving. And if we were in a space in a perfect vacuum, it would be the speed of light, that 3.0 times 10 to the 8. If it's going through air, it's a little bit slower. If it's going through water, it's also different. But it's always a constant speed. So when we measure the frequency of light, what we're doing is we're measuring the number of crests that cross a certain point in an amount of time. And usually it's 1 second. So I do like this, and I push this forward, right? Both waves are moving at the same speed, but one of those has way more crests crossing per amount of time than the other. And so all of the waves are moving like that. And something with a long wavelength, is it going to have a higher or lower frequency? Lower frequency, right? If we got more distance between the peaks, then I'm going to have fewer peaks crossing any point per amount of time. So wavelength and frequency are inversely related. Shorter wavelengths, higher frequency. Longer wavelengths, lower frequency. It's actually the difference between 2.4 gigahertz Wi-Fi and 5 gigahertz Wi-Fi. The 5 gigahertz, that's the frequency. hertz is inverse seconds. So hertz is equal to 1 over second. So 5 gigahertz is 5 million hertz, or 5 million cycles per second. So 5 million peaks per second. Is it a billion? Might be billion. Okay, so we said light can be viewed as a wave and as a particle. So we've got some particle properties of light. When we're thinking of light as a particle, that individual particle of light is called a photon. And it's a packet of light energy. We don't really go into the experiments that revealed that, but a photon is a particle of light, or we think of it as a particle of light. So the amount of energy that's carried in the packet, so every photon's energy, is determined by, or depends upon, the wavelength of the light, which means it's also dependent on the frequency of the light. So shorter wavelengths, meaning closer together, getting hit by more waves, is higher energy. Longer wavelengths are lower energy. So light waves carry more energy if their crests are closer together, or more data if it's a Wi-Fi signal. That's why 5 gigahertz Wi-Fi, if you're close enough and if there's nothing in the way, is faster. So shorter wavelength, greater energy. Higher frequency, shorter wavelength. It's also same thing, higher energy. So if we look at, this is the electromagnetic spectrum. This top part is the electromagnetic spectrum. The bottom part is actually just the part that we can see with our eyeballs. And then it's blown up so that we can see all of the colors that make that up. So we only see a very small portion of this whole thing, which is why you don't see radio waves, even though that's electromagnetic radiation, or microwaves, because it's also electromagnetic radiation, or the signal from your phone. So on here, again, zoom in on this. Yeah, low energy in the long wavelength side. You got high energy on the short wavelength side. You can see that wave at the top gets shorter and shorter. So higher energy, higher frequency, shorter wavelength. I won't test you on specific ranges of electromagnetic energy, so I won't be like, what wavelengths are X-rays? You don't need to know 10 to the minus 9 to 10 to the minus 11. What I do want you to know, though, is how these sort of sort in terms of increasing or decreasing energy. So which ones are going to be more energy? Radio waves are the lowest. Gamma rays, which hopefully we can talk chapter 17 at the end of the class, coming from radioactive decay. X-rays, we've all probably had an X-ray at least once, are also pretty high energy. But you get a relatively low dose when you get an X-ray. Talk about these. Starting at the high end of the energy spectrum, gamma rays. Shortest wavelength, most energetic. They do the most damage to tissue, produced by sun, stars, and then certain unstable atomic nuclei. This is like the thing when you talk about like nuclear fallout, nuclear reactors. Gamma rays is what everybody's scared of. X-rays are not as high energy as gamma rays. They're also less damaging. They pass through many solid substances, and they've got a ton of different medical uses for either getting a scan done to see if you broke something, or checking your teeth for cavities, or even destroying tumors. And they aren't energetic enough to cause damage, but that's why you shouldn't get too many X-rays. Getting some is fine, but you don't want to be getting like a ton of X-rays. So this is one method of radiation treatment. So you take X-ray or even gamma ray beams, depending on the treatment, and you take weak beams, and then you cross them all through the tumor. So all of the tissue surrounding gets the weak beam's exposure to the radiation, but where they're all crossing, you get a really high dose of radiation. It's a really clever way of doing it. So that's X-ray or gamma ray beams. And then mostly it's the genetic information that gets damaged. So as those cells try to replicate, their core DNA basically gets ripped apart by the gamma rays or the X-rays, and it can no longer produce new cells, and the cells die. You do damage some healthy tissue, but if it's to kill the cancer, then that's better. So that's always the trade-off, honestly, with most treatments, right? So it would be better if I didn't have to do chemo, but also the cancer will kill me or do more damage than the chemo would. So you take some risk in order to get a higher benefit. So radiation treatment. UV light. So this is just on the outside of what we can see. This is why you need to wear sunscreen. It causes sunburn, and there are a few different energy levels of UV light. I know during the pandemic, there's a lot of talk of UVC. So you could use UVC light, which is, I think, is the highest energy part of the light, or maybe it was the lowest. It's one of them. It's either the highest or the lowest, and then you would shine that on through the air in a room to kill any airborne pathogens, but also damaging enough to cause at least surface level damage to your skin. A visible light does not cause damage to biological molecules, which is good, because can you imagine if like turning on a light bulb also gave you a sunburn? That would be a very bad light bulb. And that's basically a very small portion of the electromagnetic spectrum that we can see, and it's actually hitting molecules in your eyes, which rearrange and then send a signal to your brain, and then your brain interprets those signals. Infrared light is just below visible, so infrared, it's just below red. Infra means below. This is actually the source of heat that you feel when you place your hands near a hot object. So you feel that warmth. It's not actually the air conducting that, or at least it's not, in part it is, but it's actually infrared light hits your hand, and then that electromagnetic energy gets dissipated as heat on your skin. This is also why if you're at like a campfire, if you put anything between you and the fire, it could even be a thin sheet of paper, you can immediately feel the decrease in heat because you're blocking that infrared radiation. And these also get used in night vision. So a lot of, especially basically every security camera is going to have some version of infrared night vision. You can also do cool things with infrared. So everything, depending on what temperature it is, emits some amount of infrared radiation. Hotter things emit more, colder things emit less. This is a special infrared photograph, but regular photograph, you can see this guy, two dogs. In the infrared, it's really interesting. You can see all of the warmer parts, right? So like this guy's legs, he's wearing shorts. You can see his face, shows up red. And then on the dogs, you can see their eyes, their mouths, their ears, but all of their fur for the long-haired dog is blue. It's colder. On the other dog, the short-haired dog, you can see most of it lit up in red because it's emitting more heat, emitting more infrared radiation. Those cameras are super expensive. Otherwise, I'd have one and I'd show you because they're so cool. Okay, electromagnetic. Oh, so moving down now into microwaves. It's used also for radar, and actually that's how the like household microwave eventually was made, because some dude walked in front of a radar dish that was like transmitting information to a satellite, and it melted the chocolate bar in his pocket. He's, oh, that's weird. And then, actually, this is my fun story about microwaves. The first tabletop microwave, you'll never guess what it was used to heat up. It was used to thaw frozen hamsters. So they were trying to do, this is, I don't know, 50s, 60s. They were trying to see, can we freeze people, right? Can you go into cryo sleep in sci-fi? And so they started by testing out small mammals, and a hamster is about as large as you can get before there's too much damage from the freezing. So you can freeze a hamster, and then if you carefully thaw it, it will still be alive. I'm sure there's other things that you have to do, but they found that the microwave was really good at that, because otherwise sometimes the hamsters would get burns from like hot water or from other sources of heat, but the microwave was able to evenly heat the hamster throughout. And so that's why we have microwaves at home. Now, our microwaves are not like finely tuned scientific instruments, so you end up with lava on the inside and ice on the outside. But they're really good at warming up things that have water. That frequency of electromagnetic radiation basically just hits water molecules and causes them to vibrate, and that's why it heats things up. And then the last one that we have are radio waves. So you get AM, FM radio, although, I don't know, it feels like the radio's kind of becoming obsolete. But I don't know if you've ever been on a cross-country trip and listened to radio. Has anybody ever been on a long drive? Right? You can pick up the AM radio stations. I don't know if you've ever swapped to that. You can pick those up a lot longer than you can the FM radio stations. That's because AM is in higher wavelength, lower frequency ranges, and those long waves get diffracted less when they run into things. And so they travel a lot farther. I had to, for my research, because of the pandemic, drive cross country with my boss. And driving through Wyoming, the only thing we had was AM radio because it was a really old van. That was it. Not even FM radio. There was just nothing out there. But yeah, used for a lot of different things. Basically every form of communication. Okay. Arrange the color of visible light, red, green, and blue, green, red, blue, in order of increasing wavelength. Now, if we think about the names of some of the other ones, we got infrared, and then it's visible, and then it's UV, ultraviolet, right? Violet's closer to blue. Infrared literally has red in it. If you can remember, right, ultraviolet is higher energy. It's what gives you sunburns, UV light. Infrared is lower energy. Which of these do you think? Let's talk about energy first, actually, because I think that's going to make the most sense. So red, green, or blue, which one's going to be it says increasing energy per photon. So which one's the lowest energy light? UV gives you sunburns. So you think blue? Do you think blue's going to be highest or lowest? Highest. Blue's the highest. I haven't really said anything about green. Red, though, is on the opposite end of blue. So red is the lowest energy per photon. Blue is the highest. So green goes in the middle. Sorry, say it again. Yeah, it is. Yeah, this is like visible red light, so like this part here. Visible blue light, and then visible green. But yeah, green is like right in the middle. Because red is at one end, blue's at the other. So whatever's left over has to be somewhere in the middle. Yeah. I did have a green laser pointer, but I don't think I have it with me. It's too bright. Human eye is really sensitive to green light. Okay, so that's energy per photon. So if you can work it out from infrared and UV blue, higher energy light. So what about frequency? How's frequency related to energy? Does it change the order? High frequency, high energy. So if you think about it as getting hit by waves, getting hit by more waves would be higher energy. So higher energy, again, or higher frequency is going to be blue. And what about red and green? It's the same order. All right, so blue is highest energy. It's also the highest frequency. You're getting hit by the most waves. So what does that mean about the distance between waves? Wavelength. It's the shortest. So now, according to this, we're talking about increasing wavelength. Blue is the shortest wavelength, and then green, and then red. Cool. Yeah. Oh, that's a way to remember for like visible light colors, which end they're on. Red and blue are on opposite ends. UV light is high enough energy that it gives you sunburns. Infrared means below red. It's lower energy. So if I go back to this, so this is zoomed in. So the red is actually on this end. And so just outside of red, we get infrared. And then on the blue side, just outside of that, we get ultraviolet. Yeah. So there's a way to remember those. So if you can remember those in terms of energy, then you can figure out frequency. And if you can figure out frequency, then you can figure out wavelength because they're all tied together. All right. Any other questions? Yeah. So it's like, well, it's creating that, or it's not creating that, it's producing that energy. Infrared light. More, yeah. Yes. Not create, it's the thermal energy of the molecules that make up the thing. So that's why if you heat up something metal and it's glowing red hot, if you heat it up even more, it'll glow white hot. The thermal energy is being converted into electromagnetic energy and emitting that as photons. So the thermal energy gets converted into light energy. Yeah, as a mode of dissipating energy, mostly for really hot things. It's called black body radiation. All right. So now that we know something about this, we've got this spectrum of colors. They're sorted from, we can sort them by wavelength, frequency, or energy. And especially for energy, we've got, for any of them, red on the low end, blue on the high end, everything else in between. The reason we need to know this is because that's how the Bohr model of the atom started. And so this is where we're going into, you need to know some things about this, but I'm not expecting you to remember everything about the Bohr model of the atom necessarily, just how it compares. So we've got these neon tubes. If you take Chem 1, you actually get to use these and see this for yourself. But right, neon signs, they glow this orange color. You can get different colors if you use different gases. So one of the things that Bohr noticed, Niels Bohr, is that when he looked at this mercury lamp or he looked at a hydrogen lamp through a prism, something really weird happened. Because remember, we talked about most lights they produce, or the sun even, produces all of the colors of light. Right? You get basically everything. That's why you get a perfect rainbow. When you shine this light from either the hydrogen or the mercury lamp through a prism, you don't see that. You don't see every color. So light emitted from hydrogen is basically by charging them up with electricity. Then they've got extra energy that gets emitted as light. You shine it through your prism, and instead of seeing a whole bunch of different colors, you only get 4 in the visible spectrum. And it's not like you get like a gradient of blue down to red even. You get these lines. So it's emitting a very specific frequency of light. Not several frequencies, a single frequency of light at 4 different places. So Bohr saw this and he's like, that's really weird. I wonder what happens if I look at other elements doing the same thing. So our white light spectrum, it's regular incandescent light. The sun gives you everything. Hydrogen light spectrum, there's a 4th one here on the end that's hard to see. You put helium in, and you also get these bands of single frequency light, but they're different. So like even this one down here, the first one on the left for hydrogen and helium is a little bit different. Helium's got an extra one in the middle, and then it's got a couple more. And then if you do neon, even neon, which looks red, like a reddish orange, is not just reddish orange light. In fact, there's some blue in there. There's some green. There's yellow, all the way down into the red. But even that isn't continuous, right? There's a lot of gaps in this spectrum. So he's like, all right, there's something weird going on. When I charge up these electrons with energy, the light that they emit is very specific. And so this would be mercury you get anywhere in the world would do this. So this is called the emission spectrum for an element. And basically Bohr wanted to find some way of explaining that. And so he tried basically taking the distances between these, doing a whole bunch of calculations. And what he came up with was this idea of orbits. So orbits, be very specific about the ITS here. So he's like, why do they emit specific light? Maybe the electrons are orbiting, just like the moon orbits around the Earth, just like the Earth and all the other planets orbit around the sun. Maybe they've got these orbits with different energy levels. So if I'm at this first one, n equals 1, that's the lowest energy level. And then when I take my hydrogen, my helium, my mercury, my neon, whatever, put it in this lamp, what's happening is I'm giving these electrons more energy, and it lets them jump up to a higher orbit. And at this point, they know energy is not created or destroyed. And he knows that it's in a higher energy state, and things want to get into a lower energy state. So when you excite these electrons up, they want to come back down. But to come back down, they need to emit that energy. They need to get rid of it somehow. And they do that by creating a photon. And so they lose that light by emitting a photon. So this was Bohr's idea, and this kind of explained how we saw different bands of light in hydrogen. So we go back up here for hydrogen, right? We got, remember these, 1, 2, 3, 4, 5. Oh wait, that's helium. Actually, this graph might be for helium because there's 5. So let's do that. 1, 2, 3, 4, and then 5. So those are basically the different. Oh wait, no, this is a sorry, fence post problem. It is hydrogen. 1, 2, 3, and then 4. Sorry. So yeah, 1, 2, 3, and 4. And so if I take that, and I'm going to copy it over here. That wasn't it. Bohr thought he was seeing is that when he excites an electron from n equals 1, and he excites that up to 2, it wants to go back to 1 and go back down to a lower energy. So it's jumping from 1 up to 2 and then back down again. And when it does that, it emits a photon with this light that's probably in the red spectrum, something like 650 nanometers. And then the second one was jumping up to 3 maybe, and then coming back down to 1. So it's a larger jump, means more energy absorbed, more energy released. And so that was his explanation. These electrons have these paths that they're taking around the atom's nucleus. Whenever I excite them with more electricity, some of them jump up and they jump up to different energy levels. And then when they fall back down, they're emitting that light. Now, one thing that's weird about this, and one of the key things about this, is that it's quantized. We're not getting energy levels in between those jumps. There's n equals 1, there's 2, there's 3, there's 4. There's no 1.5, there's no 1.25. There's nothing in between here. So I can only go from this lower one to this higher one. So for something to be quantized, it has fixed energy levels, and nothing can exist in between those. So this is a concept that you do need to know, is what does it mean to be quantized? So because he said these are quantized, they're fixed at these certain levels, he gave them quantum numbers. So describing this n equals 1 is the first quantized energy level, n equals 2 is the second quantized energy level. There's no in between. So it's like this weird ladder where you can stand on the first rung or you can stand on the second rung. Can't stand anywhere in between. The idea of quantization, or something being quantized, is not just the fact that going up this ladder is higher in energy, or that coming down the ladder is lower in energy. The key thing is that there are specific spaces between rungs on the ladder. Okay, but I told you this is an outdated model, the Bohr model. He did get one thing right. Things are quantized. Oh, and I guess I already explained this. But so when it absorbs energy, this is the light coming in, hits the electron, jumps it up to a higher energy level. And then when that comes back down to a lower energy level, then it emits light as a photon or a quantum of light. So that's why we get each of those different energy levels, each of those different frequencies of light. So for our Bohr model here, okay, so it's jumping up from the n equals 2. So he said going from n equals 3 and then relaxing back down to n equals 2, it's emitting this 657 nanometer, 486, 434. And notice this is from 4 down to 2. This is from 5 down to 2. Just like we said, red light is the lowest energy. This is also the lowest jump, right? Smallest jump. Blue-green is somewhere in the middle, going from 4 down to 2. Violet, or blue, on the blue end of the spectrum, is going from 5 back down to 2. So a larger jump means a larger change in energy. And actually Bohr, and I think with another guy named Rydberg, something called a Rydberg constant, they were actually able to predict these frequencies of light for hydrogen. The problem was when they tried to do anything else. So it was great because it predicted these lines of the hydrogen emission spectrum for hydrogen. But let's do helium. And then it fell apart. It didn't work anymore. So they were missing something. They could only do it with something with one electron. So that's why this got replaced eventually with the more sophisticated model called the quantum mechanical model. So the orbit was not quite it. But he did get it right that things are quantized. So the quantum mechanical model that replaced it came up with this new term called orbitals. The difference between an orbit and an orbital is an orbit is a specific path. It's that circle. And it goes round and round the circle. You could time it. It's like running laps around a track. Orbitals are probability maps that show statistical distribution where the electron's likely to be found, or like a heat map. So when you look at an orbital, it'll be a 3D shape that'll be a sphere, and it's denser in the middle, and it's less dense on the outside. I actually think we'll talk about it. But it's where is the electron most likely to be found? more likely to be found in the middle, less likely to be found on the edges. So those are orbitals. So we have an analogy for what exactly that means. So if you think of baseballs as electrons, an orbit, like a pitcher throwing the ball, right? The batter can hit the ball because he can see where the pitch started from, and he knows that it's going to take a pretty much, unless the pitcher's throwing curveballs or other things, right? If he's just throwing a fastball down the middle, the batter sees the ball, he sees it leaves the pitcher's hand, he can predict where that's going to be because he's been swinging at balls his whole life. And the human brain is just really good at predicting trajectories. So he sees the ball leave, it comes in, he should be able to hit it. Electrons don't do that. So if this pitcher was throwing electrons and he threw an electron every time, it would land somewhere different every single time, no matter what he did. Even if he mixed things up, it would always land in a different spot. So we look at this sort of weird batter's box. So the pitcher's throwing the ball. Sometimes it's coming in a straight line, and then it basically, when it leaves his hand, it disappears, and then it reappears in one of these spots, in essence. The best chance for hitting the ball is inside of this 20%, because that's the highest density. But 40% of the time, it could be in this larger region. 70% of the time, it could be everything inside of this. But you can't predict really on any single pitch where it's going to land. You could just say, on average, 70% of them are going to land in here, which implies that like 30% of the time is pretty likely to hit the batter. So this is part of the wave-particle duality. We can see the particle land, we can't really predict its path. So in orbit, again, it's a circular path showing the motion around the nucleus. It's predictable. An orbital is a probability map, meaning it's an area in which we say that it will probably be, and they are completely unpredictable. You cannot predict where the electron is going to be at any given moment. This is where things get weird, because how is that possible? Quantum mechanics, quantum physics. So orbits, predictable, but orbitals are unpredictable. And when we talk about orbitals, we give them a specific number and a letter, and this is related to the crazy math that goes into calculating these probabilities. So the principal quantum number, we just call n. And so if you think of this as like an address, n is like the city where the electron could be. N increases as n increases, so 1, 2, 3, energy increases, so higher and higher energy levels, again, specifying just different cities. And then we also give them a letter that's associated with the subshell. So you got n, which is this principal quantum number, and then we have subshells, which could be S, P, D, and F. You can maybe think of that as like a neighborhood inside of the city. So if I say something as n equals 1, then we've got this larger region, that's n equals 1. And then if I say S, then maybe this smaller region is S. These regions out here are all P. And then we've got ones in between. Those are D. And so there's these different regions around it. And so we say n equals 1. Got all these different neighborhoods in here. So n equals 1. And then my subshell is maybe S. It's that one in the middle. And so it's a region that it could be in. All right, so how does this apply at all to atoms, right? So 1s is the orbital that's the lowest in energy, and it's shaped like a sphere. So this is what I was talking about, a probability density map. You can imagine this as being if you took a picture every second for like 10,000 seconds, and each dot is where the electron was in each of those pictures. And so it can jump all over the place. It can be in any of these spots. You can see basically outside of this line, basically, I'll do it this way, about 0% chance, it's not 0, but there's almost a 0% chance that it's outside of that sort of region. And so usually you'll see this as this sphere, actually even without these dots on it. So basically, 95% of the time, it's inside of this sphere somewhere. And that's the s orbital. Could be outside of there, 90% of the time. 10% of the time could be outside of that shape. Electrons are weird. And we're going to add a couple more. They do want you to know the shapes of. But this first orbital, the 1s orbital, that's the single electron in hydrogen. So since that's the lowest energy, it's called the ground state. And electrons will generally, like most things, seek out the lowest energy orbital available. If you give it enough energy, that electron will jump up to some other energy level. That's an excited state, and then it'll come back. I don't know why I've never remembered this joke at this moment before, but what's a cow in its lowest energy state? Ground beef? That's the appropriate laugh. That's the appropriate laugh. The ground state's lowest energy. The excited state is unstable, wants to go back to that ground state. Okay. So the s orbitals are pretty simple. 1s is a sphere. 2s is a bigger sphere. Can anybody guess what 3s is? A bigger sphere. So all the s orbitals, they're the simplest. They are spheres, essentially. And as you go to higher energy levels, you're getting farther away from the nucleus. They get larger. Actually, it takes higher energy to have electrons in those higher shells. So this is why hydrogen is in the 1s, its electrons in the 1s. It wants to be as close to the nucleus as possible. If you think about this too, remember we've got a nucleus which has a positive charge, and we've got these electrons with negative charges. They want to be as close together as possible so that their charges can be as neutral as possible. The farther away that those get, the more energy it takes. Okay, s orbitals are spheres, n equals 1. You got s, n equals 2. You've also got 2s, which is slightly larger. 2p, shapes get a little more interesting. So the 2p subshell has 3 orbitals. So 3 separate places that can hold electrons. They each have the same shape. And if we draw out a coordinate system, we got our x, y, and z. Each of those orbitals is on one of those axes. And we label them something like this, where it's p sub x. So that's the p orbital on the x-axis, the p orbital on the y-axis, and the p orbital on the z-axis. And really, those are all relative to each other. So it's a different shape. But similar to the s orbitals, what do you think happens when we go up to 3p? It gets larger. It's the same shape, just a little bigger. 4p, same shape, again, just a little bigger. So they have these different orientations, and then they also don't overlap with each other. You can see there's actually in the middle, there's 0 probability of being exactly in the middle. So the electron can be on one side, and then it can be on the other side, and it doesn't have to cross between. So there is a pattern to these shells, just like there's a pattern to most things. In our lowest energy level, n equals 1, we only have s orbital, the 1s orbital. If you go up to n equals 2, we also have 2 subshells, s and p. If we go up to 3, n equals 3, now we've got s, p, and d orbitals. If we go up to 4, we've got s, p, d, and f. We're not going to go all the way up to f. We'll just talk through d orbitals. Now the d orbitals, again, s was simple, it's a sphere. P is a little bit more complicated, it's these 3 dumbbell shapes. D now, which is on the next slide, is even more complicated. And now there's 5 different subshells. And they all have this sort of X shape. And so like the p orbitals, each one was on an axis, x, y, and z. The d orbitals are each in their own plane, aside from the last one, dz squared, which is the dumbbell with a donut. So it's this X shape on the YZ, again, the X shape on the XY. This is kind of like laying flat. XZ, which is going forward and back. And then the X squared minus Y squared has one of those on the X and Y axis. So things start to get more and more complicated as you go to higher and higher energies. And I basically, for these, expect you to, if I gave you a picture of one, I don't expect you to be able to draw these. But if I gave you a picture of one, you could tell me, oh, that's a d orbital or a p orbital or an s orbital. Not on this test, but on the next test. Okay, so I said that we would get to, oh, well, we got a little bit farther than I thought we were going to. We would talk about, like, how does this matter for any of the other stuff that we talked about, right? So far we haven't said, like, how does this explain anything? The main thing it's going to explain is charges. And so the last thing we need to talk about before that are these things called electron configurations. So an electron configuration, we are not all artists. We're not all so gifted. So it would be really hard to, for any given atom, draw out all of these orbitals that have electrons in them. And besides, these sort of stack on top of each other, right? If I have a 4D orbital, it's this exact same shape and these exact same orientations, but larger. So drawing things on top of each other is really confusing. So instead of doing that, we have something called electron configurations. And an electron configuration is basically saying, in this orbital, so this energy level, in this orbital, I have how many electrons? So my 1s, again, that's a sphere. So 1 is the principal quantum number. So lowest energy in the s orbital, I show the number of electrons as the exponent. So 1s with a superscript of 1, or exponent of 1, means 1 electron in the 1s orbital. So that's what hydrogen's electron configuration would be. This is probably one of those things that's going to seem... Actually, let me do this first. So if I do helium, that's also 1s. But now helium has 2 electrons. We can put both of those electrons in the 1s orbital. I guess there's a couple more things we got to talk about before we can really do more electron configurations. Another way to show this are orbital diagrams. So again, for hydrogen, the 1s, 1 electron. So same as the electron configuration, that was 1s1. Electrons have a property called spin. So this is written as a half arrow up. That half arrow means it's a up spin. There's up spin and there's down spin. They're not literally spinning, but it's called spin. So the orbital diagram just shows us the spin of the electron in that orbital, and this will be relevant when we start adding more electrons. Because of something called the Pauli exclusion principle, which says that orbitals may hold no more than 2 electrons with opposing spins. And really what it boils down to is 2 electrons per orbital. So if I do helium again, helium's going to be 1s2. So if I draw this out as an orbital diagram, it's 1s. And then I can have 1 electron spinning up, and I can have 1 electron with downspin. So upspin, downspin. And that would be a full orbital. Sorry, I haven't paused for questions in a while. Are there any questions? Yeah. The electron configuration? Yeah, the S2. Yeah, we'll talk about that. That's coming up. That's also coming up. It will be relevant soon. Yeah, we're still getting there. There's a lot of lead up into this. Any other questions? Should we just keep? I'd like to maybe get to a few more examples of this. Okay. So for now, again, remember we've got, let me write this out again. So we got n equals 1, that was the lowest energy. And that has the s orbital. If I go up to n equals 2, now I've got s and p orbitals. If I go up to n equals 3, then I've got s, p, and d orbitals. So right now we're just doing helium. So we do helium. Helium, it's in the same row as hydrogen. So the periodic table is actually the, I don't really want to call it a cheat sheet, but it's basically a cheat sheet for this. So the first row is n equals 1. So everything here is going to be 1. And since we only have the s orbital, hydrogen has a 1s orbital, helium has a 1s orbital. When I go down to the second row, that's n equals 2. So n equals 2 has s and it has p. So lithium has the 1s underneath, and then it's got the 2s on top of that. And then by the time we get over to boron, we start adding p orbitals. So the reason I know helium has 2 electrons and is in 1s2 is because it's in the first row. So that's the 1. It only has 2 electrons, so that's going to be s. So if I go back to this, 1s with 2 electrons. And so then the orbital diagram would be 1s, and then 1 electron up, 1 electron down. And then for lithium, the way this is going to work is everything builds on top of the things before it. So if helium has 1 more electron than hydrogen, then lithium has 1 more electron than helium. So this should have 3 electrons. But when I go to put those electrons into orbitals, because I know we just talked about it, but the Pauli exclusion principle means I can only have 2 electrons in an orbital. So if I do 1s, I can have 2 electrons there. But I can't put that 3rd electron in. So it has to go into whatever the next orbital is. So the next highest energy orbital, or next lowest energy orbital, will be the 2s. And I have 1 electron left over, so I just put the electron in there. So 2s1. And the 1s and the 2s both can hold 2 electrons. So my 1s electron, or my 1s orbital, will get 1 up, 1 down. And it doesn't matter if this is up. When you put one in by itself, it doesn't matter if it's up or if it's down. I just default to up first and then down second.
Again, where you got the 2 from on the 1s? No.
Oh, this one.
Yeah.
The 1s2. It's because, if we go back to the periodic table, how many electrons does helium have? 2. And then lithium, and again, we're talking about all these without any charge, so lithium would have how many electrons? 3. So if I went to beryllium, how many electrons? 4 electrons. It's not on this slide, but let me do beryllium. So that's also going to be 1s2. And again, I've used 2 of the electrons, so now I got to go up to 2s. And beryllium has 4 electrons, so that goes 2s2. So 1s and 2s, both with 2 electrons. Okay. We're going to keep expanding out the periodic table. I'm telling you here, the periodic table is an incredible cheat sheet for doing these electron configurations. It basically tells you based on where it is on the periodic table. Yeah, that's fine. We'll pick up on Thursday.